Thank you all for your patience and understanding this week. Migraines can be very unpredictable, and the light-sensitive variety is particularly detrimental, especially when you have numerous online courses and spend many hours a day in front of computer screens. But enough about that. The intention for this video today is to cover our remaining slides on the topic of multiple regression, which should get you ready for the lab section this afternoon. Since you all have busy schedules and I've already kind of mixed those up enough, I'm going to be giving you most of this afternoon's lecture period in order to watch this video so that you have time for sure to get through it before the lab period. But I'm also going to be around to answer any questions that you might have on this topic, so I'll still be present in Zoom, at least for the first part of the day, and I'll make sure that I'm still around if you have questions throughout, but I'm not going to try and give another full lecture during that period because I want to make sure that you have time to see this multiple regression topic first. So we left off having discussed simple regressions. We were looking at statistical models where we have only one outcome and one predictor variable. And we walked through the process and saw that it was effectively a more complicated way of conducting a correlation, just with slightly modified framing, but the math and everything underneath was all effectively the same. So now we're going to make things a bit more complicated, but hopefully we'll also see how conducting a multiple regression can pay off and give us additional useful information. So we'll start by looking at a linear model that's in a similar form to what we've already seen, but this time we have two predictors rather than just one. Looking at this model here, we see that we still have our observed outcome variable, that y value, and we also still have our b0, which was our intercept, but the definition for the term in this situation with two predictors is slightly different. So instead of just being where that regression line crosses the y-axis when x equals 0, now we have to keep in mind that we have two different x's, x1 and x2. So now this b0 is the predicted value of y when both x1 and x2 are equal to 0. So this is a lot harder to think about because we can no longer easily graph this, because now we're looking at three different variables and we're getting into some multi-dimensional stuff. But, so this is still the same basic concept, but now applied to more and more complex dimensions. So it's still the point at which the regression line is crossing the y-axis. We've just adjusted which x's we're talking about. So instead of just x in general, we're now looking at both x1 and x2. And then as we look at more complex regressions, we could have three or more of these predictors, so we can add more x's as needed. We also might note that we now have two slopes instead of just one. So we have a b1 and a b2. So b1 is going to be the change in y per unit change in x1, specifically when we control for x2. And sort of continuing on from that, b2 would be the change in y per unit change in x2 when we control for x1. So the part that we care about here is the fact that it's still the slope, still looking at the change in y per unit change in something about x, but because we have multiple predictors, we're specifically controlling for the other predictor. And these slopes are probably the aspect that we care most about when it comes to multiple regressions because they specifically reflect the direction and strength of a relationship between our outcome and each predictor variable while controlling for the other predictors. So this is really useful information to have in regards to our model. And then at the end here, we also still have our error term, and it's going to be interpreted in the same way. We're still looking at our residuals, and it should still come out to summing 0, especially if our data is nice and normally distributed. So that's the ideal, which might matter a little bit later on. You should have been able to go over checking assumptions for regressions in R with Christine last week. Checking these for multiple regressions is going to be the same as doing it for simple regressions. You're just effectively looking at more variables. So you have access to some R code going over the process for both simple and multiple regressions. This might be the same as what Christine used or slightly different in terms of notation, but the overall concept is the same and we're still looking for the same things. Before we actually run the linear model, we can look at the distribution of the data to get a feel for some of our assumptions, but many of them can't actually be tested until we run the model and look at our residuals. So once we've run the model, once we've used that LM function, then we can ask if our errors are independent. So that's the first of these assumptions that we might want to test. In the R code, we are looking at misclicked there. We're looking at sort of these check model diagnostics. So we're starting here. The first step is to run our linear model. So that's the LM on the data from the previous time from assignment 3. So we're just calling it W6 full. And then we're going to look at DWT. So this is a Durbin-Watson test. And this is specifically meant to look for the independence of our errors. So we're looking specifically here, so we see that it's looking for autocorrelation, which is basically saying that it's looking for dependencies within the data. So they're looking for non-independence. So we're looking here at our p-value, and what we want is a non-significant p-value, which ends up indicating independence. So if we had significance here, then it would have detected autocorrelation, and then we'd have a problem because we're going against that assumption of independent errors. We can also plot our model using the plot function here, and this allows us, actually run it. So this allows us to actually test things like normal distribution, checking if the model is linear, and if it has homogeneity of variance. So when using this plot function on a multiple regression model, you're going to have to come down here into the terminal window or into the console window, pardon me, and hit enter in order to see each of the graphs that it's trying to plot up. This first plot looks at our residuals versus the fitted values, meaning that we're looking at the value predicted by the model plotted against the error that isn't explained by that model. So in this case, we're looking for funneling to see if the variance is even across the model. We also want to check for systematic variance from a line. So do we see U-shaped data or anything weird going on here? And if not, then we can advance to our next plot. And our next plot is a QQ plot. So this is where we're evaluating whether our residuals are normally distributed. So we make sure that our tails aren't deviating too far from the line and nothing looks overly concerning, so we can probably continue on. And the last two of our plots are just looking to help us identify any problematic data points like outliers, things that might be skewing our regression model. So we're looking for data points that would be way off on their own, far away from the rest of the data. So we can look at this one here and this one as well. We don't care too much about the specific axes and stuff, but what we would be looking for are points that are very, very far off, and we don't really see anything that's too troubling here. So if we had outliers, especially for a class like this, we'd point to something that would be sort of off the page. It would be so extreme, but here nothing looks overly eye-catching, so we can call that pretty good. In our last lecture, we had looked at our model output and pointed out what each of these sections told us. For multiple regressions, we're going to care a lot about the model fit, which is going to be addressed in the area within the red box here. So this will tell us if we have a model that significantly explains the variation in our outcome variable. And in cases where we have multiple possible models, we will be looking for the one that best fits our data. And so this section allows us to evaluate how well each of our models fits the data in question. At the top here, we have information about the residual standard error, but that's not necessarily super important to us. What we care most about are the other two lines. So our multiple r squared in this case is 0.2114. And this tells us that together, self-esteem and narcissism will explain 21.14% of the variance in antisocial behavior in this particular data set. However, because we have two predictors, we need to keep in mind that some of the variability that's being explained here may be explained due to chance. So our adjusted r squared just takes that extra variability into account, specifically based on the number of predictors in our model. So in this case, we have two predictors, so that's what it's using to make this adjusted r square value from what we had originally calculated. For our information about statistical significance, we have an F statistic here at the bottom of the box. For our degrees of freedom, we have 2 and 247. So if you recall, an F statistic is actually a ratio between the variance that is explained by the model and the variance that is unexplained by the model. So the unexplained variance has 247 degrees of freedom because we have 250 observations minus our two predictors minus 1. And for our explained variance, that has 2 degrees of freedom simply because we have two predictor variables. So, and in this case, we have our p-value listed here, and this is a very significant model because this is a tiny p-value. So, times 10 to the negative 13, so very, very tiny here. We would probably report this as less than 0.001, unless you wanted to go into lots and lots of details there. Once you've determined that the model fits your data well, then we can consider it worthwhile to start interpreting our model parameters. You don't want to spend a ton of time looking at these if the model doesn't fit your data well, because a poorly fitting model isn't overly useful and the parameters would have very little meaning, so it would be a pretty big waste of time. But now that we've looked at how well this model fits our data, and now that we're satisfied with how significant this fit is, now we can start looking at our coefficients and some of the other information that's in the rest of this model printout. As we noted earlier, we're going to care mostly about the slopes. So if we look at self-esteem and we look at the slope here, we see that self-esteem has a negative relationship with antisocial behavior, specifically when we control for narcissism. And if we move across here, we see that this is again a very strongly statistically significant relationship. We can then look at the effect or the relationship between narcissism and antisocial behavior, specifically controlling for self-esteem, and we see that it's a positive relationship, so no negative sign for this one, and again, it is very strongly statistically significant. So two statistically significant relationships here between these predictor variables and our outcome variable when controlling for the other predictor variable. And just like we did before using or in our simple regressions, we can use the LM beta function to convert our coefficients into standardized coefficients. So this would allow us to compare between different analyses, between different models, and even between different data sets. So here we have 1 unit increase in self-esteem should correlate or have a relationship with a negative change of 0.50 unit change for Y. And we also have our standardized coefficient for narcissism, so every unit change of narcissism would correlate with a positive change of 0.29 in. So again, Same basic idea where we took our original coefficients, but now we have standardized them so that we can compare them between different analyses. For your reference, here are the formulas for calculating those regression coefficients when there are specifically two coefficients in the model. As you might notice, this isn't overly practical. As we start adding more predictors into a model, this very quickly gets out of hand, to the point where you couldn't reasonably calculate them manually. So rather than focusing on the equations themselves, I'll just remind you of the fact that our unstandardized coefficients are still in the units or scale of whatever you originally measured those variables using, and the standardized coefficients are in standardized units.